everyone. Well, I don't see you, but it's great that you're all here for this youth talk session of ICANN X. So my name is Bart van der Stam, and we have a very nice session for you today. So first, a little bit about me. I'm an assistant professor in the Netherlands, Utrecht University, since 4 years now, and I work on electrocatalysis and in situ operandi techniques, mostly spectroscopy and X-ray characterization, to really understand this interplay between the surface and the reactants, in this case CO2 often, and how we can play with the materials to really tune this reaction into the direction we want to make value added products. And ever since I work in this field, since 4 years, I've read many nice articles, of course, and you start to see patterns. So you start to see common names, and that's why I thought for this session of the youth talks, I really wanted to invite these three speakers. So Reshma R Rao, Mariana Monteiro, and Paula Sebastian Pascua, because I've read their papers with many interest, and they work on related topics, but still they have different angles to similar problems that we all face in electrochemistry. So that's why we unified it as studying electrolyte interfaces. And I'm really happy to have the three of them here. I follow them on Twitter. We met sometimes in real life, but it's really impressive to see what they have already accomplished during their PhD and postdoc. And now they're all independent group leaders in different places, building up their own research groups. So I think it's an amazing opportunity for me to invite them, but also for them to show their very interesting work to such a wide audience. So without further ado, I would like to give the floor to the first speaker, but not before I introduce her properly. So it's Reshma Rao from Imperial College London, and she can read in the abstract. She will discuss time-resolved optical spectroscopy to study photo and electrocatalysis materials, because these fields are related. Sometimes you also have photoelectrochemical systems, and the problems are also similar in this case. So the questions that we have in these different fields, they are quite similar. She has won a lot of prizes the last year, if I see that on Twitter. And since October 2022, she is starting up her own independent career at Imperial College London. And with that, I would like to give the floor to Reshma, and we look forward to your talk.
Pleasure of the work that we're doing, and today I'll be presenting some of the most recent work that we're doing at Imperial College. I'll mostly focus on electrocatalysis, but as Ward mentioned, a lot of this can also be translated to photoelectrocatalysis as well as thermal catalysis. So I don't think I need to introduce too much to this audience the need to achieve net zero, and particularly considering the number of new energy users we'll be having, and people transitioning towards having a higher standard of living and requiring a lot more energy. It's really more important now than ever to be able to start decoupling the CO2 emissions with energy production. And that really brings me to what I'm really interested about and research about, which is particularly creating green energy vectors. And one of them is hydrogen. And this is data particularly from the UK, where I'm based, but I'm quite sure that looking across the world, we have similar plans and trajectories for increasing, for example, green hydrogen production going all the way to 2030 and even 2050. So green hydrogen is particularly interesting as a net zero energy vector because it allows us to decarbonize really challenging sectors of society. So heavy duty transport, for example, many industrial applications. So it's a really exciting emerging energy vector. But we want to be able to produce green hydrogen at the terawatt scale to enable this decarbonization. And one way we can do that is by taking either solar or wind energy and using that to split water, which is earth abundant, into oxygen. And you can do that using this electrolysis setup. So you form oxygen at the anode, and you reduce the protons that you form at the cathode directly to hydrogen. Now, if we see where we have the losses in this kind of electrolyzer technology, it becomes quite apparent that to draw a significant amount of current density, we really need to overcome this huge overpotential which occurs at the anode. So the real emerging question in catalysis is, well, can we try and identify the mechanism for water oxidation on state-of-the-art metal oxide catalysts and use that information to design more active and even more stable catalysts for this reaction? So traditionally, about 2 or 3 decades now of catalyst research has been able to model the water oxidation mechanism on metal oxides using this very simplistic approach where you have a single site. You absorb water on it and deprotonate it to form OH. You deprotonate that again to form this oxo species. This is when you have the absorption and deprotonation of a second water molecule to form these OOH species. And finally, the last deprotonation step results in the evolution of oxygen. So this is a very simple single site kind of mechanism. And it differs a lot from how photosynthesis and the oxygen evolving complex, for example, in photosystem 2, which is what plants use to do the same reaction. It's very different to how that operates, right? So here we have 4 different manganese centers, and in each step of the reaction, essentially a manganese center is oxidized all the way going to this S4 state where you have 4 oxidized manganese centers, and then that can trigger the evolution of oxygen from this very oxidized complex. And in fact, recent studies, and this is now looking at a state-of-the-art iridium oxide electrode, was able to show that in fact building up these oxidized species is also important for driving catalysis on some of the inorganic electrocatalysts, kind of mimicking this mechanism from photosystem 2. So the idea here is that as you oxidize the surface, you start reducing this activation energy for the water oxidation reaction. Now, some of our own work, both electro and photoelectrocatalysts, has shown that in fact building up these oxidized species is important to be able to trigger this rate determining step of OO bond formation for water oxidation. But it's still quite unclear how the actual kinetics of this reaction take place. So the real question then becomes, from a very mechanistic and fundamental standpoint, is, well, can we quantify the density of these different oxidized species, especially within the water oxidation regime, and can we directly relate this density of these oxidized species to the reaction rate and use that understanding to get some more mechanistic insight of what happens at these very complex interfaces. So at Imperial College, we've developed a new optical spectroscopy toolkit, which is time resolved and collects data very quickly. But essentially, what you're doing is you have a light source, you have loads of mirrors, which have avoided in the schematic, but you're essentially measuring at the same time how the current changes as a function of potential and how the optical absorption of the sample changes as you apply this potential. And it's only by correlating these 2 different data sets can you directly understand how changes in electrochemistry correspond to changes in the optical absorption. And this principle essentially relies on the fact that most metal oxides, especially most of the catalytic metal oxides, are in fact electrochromic. And what that means is that they change their color either when you polarize them anodically or cathodically. And you can see these are some of the metal oxides which are used in these electrochromic windows that change color depending on the voltage that you apply across them. So like I mentioned, we've developed this setup at Imperial College, which has a CCD camera. It's cooled to liquid nitrogen. temperatures, and that essentially eliminates thermal vibration noises. It's fast. You can get spectra in milliseconds and microseconds, and that essentially enables us to really get a large data set as we either apply potential or as a function of time. And finally, we can do measurements in different types of ways. You can either do measurement in the transmission mode where the light goes through the sample, or if you have a non-transmissive sample, you can do measurements in the reflective mode, for example. So today I will be looking at two different examples. First, looking at doped nickel oxide for alkaline water electrolysis, and in the second half of the talk, I'll be looking at iridium oxide and seeing how we can apply this technique to understand something about acidic water electrolysis. So with nickel, with the nickel oxide catalysts, which are fairly active in alkaline solutions, a lot of the literature has already reported that doping the nickel oxide significantly changes the catalytic activity, and particularly being able to dope it with, for example, 10% iron in this case, significantly increases the activity of the catalyst. So you can see the undoped catalyst has really poor activity. It's this purple trace here. And the real question we had was, well, what do these different dopants do in terms of modulating the activity, and can we rationalize these trends that we're seeing here? So we started out by looking at the cyclic voltammogram, and we see we have this really prominent redox transition, which essentially corresponds to the deprotonation of these OH groups. There's really excellent work, for example, by the group of Mark Koper, which has been able to identify that this redox transition is essentially the deprotonation of these OH groups to form these oxo groups on the surface. And here you can see, for example, in the case of manganese oxide, this transition is about at 1.35 volts or so. But as you change the dopant in this order, going from left to right, you shift this redox peak position to more and more anodic potentials. And what that essentially suggests is that these oxo groups tend to possibly bind to this manganese center a lot more strongly. So you form them at lower potentials compared to, for example, the undoped nickel oxide case. So we want to try and understand what these different redox transitions are, and we can do that by looking at optical spectroscopy as a tool here. So we see that as we go over this redox transition, as we scan the potential more positively, we have an optical spectra which looks something like this, with a peak at about 475 nanometers or so. Now, as you finish scanning through this redox transition and continue polarizing your electrode more positively, what's really interesting is we see the evolution of a different spectral feature which absorbs at slightly larger wavelengths. And what this in fact suggests is that there's possibly a different redox transition happening at higher potentials. Two different phi spectral features evolves as you apply a positive bias. So in this case, for example, if we start applying positive potential from 1.5 going up to 1.6 volts, we not only have these features with this dark gray trace here, but in fact, the density of absorption keeps increasing with the potential, as we can see here, which really suggests that these species grow in number as you're applying the potential. We want to try and quantify the density of these species, and in order to do that, we look at transient absorption spectroscopy. So essentially what we are doing here is applying a step potential. You start with V, apply a step potential V1, and come back, step down to potential of V. And you can measure with pulsed voltammetry. You have a curve that looks something like this. You have this positive charge when you step up. You have this negative charge when you step down. And at the same time, you can measure the change in optical absorption at a given wavelength, for example. So you can see as you step up, you have this increase in absorption. And as you step down in potential, you have this consequent decrease in absorption. Now, as you increase the potential step that you're taking, you have a much larger charge transferred because of the oxidation or the subsequent reduction of these species that you're forming, and you have a higher density of optical density that you measure. So in fact, if we do a couple of these measurements, what we in fact get is a direct relation between the optical density and the charge passed in the sample. And what that then allows us to do is essentially go to any optical density that we have in a plot that looks something like this, and turn that into the number of electrons per geometric area. And that's really informative because now we can collect all of this optical data that we were looking at and essentially plot it as a quantified number of oxidized species as a function of potential. And so we see now that we can not only quantify the fact that there's this second oxidation within the water oxidation regime, which possibly corresponds to the deprotonation of the second OH groups on the surface, but we can also start quantifying the number of these oxidized species that are forming. And this essentially corresponds really nicely to the trends in the redox peaks that we were seeing, where for manganese, this redox peaks was at the lowest potential, symbolizing that we have oxo species binding very strongly to the manganese surface and going all the way to the undoped and the zinc-doped oxide, for example, where these species tend to bind more weakly, and this second redox transition is pushed out significantly into the water oxidation regime. So now that we're actually measuring the number of these oxidized species that are forming at these high potentials, we can directly be able to relate them to the current, which here we define as the number of oxygen molecules, for example, as a function of these oxidized species per second. So if we do that, we can relate the current to the density of these species. And here you see that I've plotted it as a log plot of the current versus these species. And we see that across the different samples, we have a constant slope of about 2 over an order of magnitude of increasing current density. And what this essentially suggests is that we have a possible kinetic model that looks something like this, where the current trends as a square of the density of these oxidized species, essentially implying that if you then took the log of the current, it would scale with the log of these oxidized species, and the slope would be 2, which is exactly what we see. And mechanistically, what we think that means is that you have these oxo species that form as a function of potential, especially at water oxidizing conditions, which is what we probe with optical spectroscopy. And this slope of 2, in fact, suggests that you're possibly accessing a coupling mechanism between these species to evolve oxygen. So based on this, we propose a reaction pathway where you have these nickel centers that get hydroxylated during that first redox transition. In the second redox transition, you start forming these different oxo groups, and we can see that by the increase in optical absorption under these potentials. And in fact, because we see this slope of 2 in the previous graph that I've shown you, we can assign the rate determining step to be the chemical coupling of these 2 different oxo species to form an oxygen molecule. So based on this information, we can then start to rationalize the trends in catalytic activity for these different doped metal oxides. So here we see that we've plotted the turnover frequency as a function of the redox peak potential, which is a proxy for how strongly these oxo groups are binding on the surface. So we see iron is on top of that volcano plot, and as we go from iron to manganese, for example, these oxo species tend to bind too strongly to the surface. So in fact, getting them off the surface via this rate determining step is what limits the overall kinetics of the reaction. On the other hand, we see going to, for example, the undoped to the zinc-doped oxide, these oxo species bind fairly weakly, so forming them in the first place is what determines the overall rate of the reaction. And in fact, for iron, we see that these oxo species bind neither too strongly nor too weakly. So you're in the sweet spot for being able to form these oxo species and create these intermediates that are essential for the catalysis, but not form them too strongly so as to start limiting their coupling and desorption from the surface. So this was a great way for us to start thinking about how these catalysts operate and what really modulates their activity. But it was really reassuring for us to see that some of these samples that we'd grown on these FTO substrates to be able to do the operandi spectroscopy, in fact, actually hold the same trend when you start depositing them on three-dimensional metal supports to be able to access really high current densities. So it's reassuring to be able to see that a lab scale trend also holds under more industrial settings. So for the second example, I will be looking at iridium oxide catalysts, specifically for acidic water electrolysis. And here we can see a cross-sectional schematic of electrolyzer, and this is some great work from Hubert Gasteiger's group, and it's quite striking because we can see that here we know the oxygen evolution has really poor kinetics, but here it's quite striking to see how thick a layer of iridium oxide you need in acidic electrolyte to be able to drive this reaction. And iridium is a particular concern because if you look at the price versus annual production of different metals, iridium is really at this unfavorable position of being of having really low annual production and really high price. So that really limits, for example, scaling up these technologies to the terawatt level. So we started by again thinking of how can we apply these optical spectroscopic techniques to iridium oxide, and we started off with this really ill-defined electrodeposited iridium oxide. And here you can see the cyclic voltammogram, and see we can already start to identify a few different redox transitions just based on looking at that cyclic voltammogram. So we look again at optical spectroscopy, and unlike the nickel case here the spectra is a bit more complicated. You have an evolution of a few different spectral features, and we can break that out into the spectral feature at about 600 nanometers at low potentials, followed by a spectral feature at about 750, 800 nanometers, and finally the spectral feature at about 500 nanometers at high potentials. And these essentially correspond to the different redox transitions on the iridium oxide surface. So we can go in and fit the overall data with these three different spectral components and see that now we can start to quantify the density of these different redox transitions as you apply potential. And that's really informative because while people had predicted and known that iridium oxide in fact does exhibit this electrochromism as you apply oxidizing potentials, here we've been able to use that property to actually determine the density of these species that we are forming as we apply potential. So we were curious about where in the material, especially considering this is a really ill-defined metal oxide, where in this material do these redox transitions occur? So we look at a technique which is called time-of-flight secondary ion mass spectrometry, where essentially we take our sample, we cycle it in deuterated water, and then measure the density. We then sputter through the sample with our analysis, and then with our analysis beam measure the density of deuterium to hydrogen ions that were evolved. And here we can see, as you sputter through the sample, it's only about in the first 100 seconds, which corresponds to 20 nanometers or so, that we have an enrichment of deuterium, which really suggests that it's about 20 nanometers of the sample that's catalytically active in this case. And that's possibly the case because it's a really amorphous oxide. We've done since then similar measurements on a crystalline oxide and found that in that case the reaction is really confined to the very surface of the catalyst. So we wanted to see how, if we zoom into this high potential, we want to see that we are forming these different redox species, and the real question we had was, well, how quickly can these redox species oxidize water? So what's the kinetics of water oxidation on these redox species? So in order to do that, we can look at open circuit decay measurements. So essentially what we are doing here is measuring the coverage of these species at a voltage of V1. We then increase the potential to V2, which is a higher potential where we have a higher coverage of these oxidized species. and then essentially let the system decay to open circuit conditions. And it's this rate of initial decay which tells us how quickly these oxidized species can oxidize water to oxygen. And this, in fact, is not new. This is seminal work, for example, by Conway in the 1950s, where they used this open circuit decay concept to measure the first Tafel slopes on nickel-based oxides. But in fact, the additional bit of information that we can do now is not just measure how the potential decays, but measure how the spectral shape decays and get more information about what states are actually driving the catalysis here. So here we can see an example of the spectral decay, specifically at 460 nanometers. And from this data, we can see quite nicely that at low potentials, you have this really long time constant of decay, but it's only as you start increasing the potential that this time constant for decay starts getting faster and faster. So we can quantify that decay time as a function of potential, and in fact, the quantified numbers match very, very well with what we can see just with our eyes, that as you're increasing the potential, this decay time is getting faster. So what this shows in a very simplistic picture is that you have these iridium centers. We've measured with optical spectroscopy the formation of these really oxidized iridium states. And then we can see that as you increase the potential and form more of these states, you increase the kinetics for water oxidation. And in fact, we can then go in and directly create an analysis where we now relate the turnover frequency as a function of the coverage of these different oxidized states that you form. And here, in fact, we see a slightly different trend from what we had for the nickel-based oxides, where now the turnover frequency scales exponentially with an increase in the coverage. And that, in fact, can be modeled using this equation here, where the current scales exponentially with the coverage. And it really goes back to this initial picture with this really amazing work published a few years ago now in Nature, which essentially suggests that it's the coverage of these oxo species that determines the activation energy. And that's exactly what our data shows. As you increase the coverage, you exponentially change the turnover frequency, and it follows this predicted model really, really well. But this is for a very heterogeneous iridium oxide surface. If we really want to go in and pinpoint that in fact it is the coverage of these oxo species that is responsible for the catalysis, a nice way to do that is to compare this electrodeposited oxide with molecular iridium dimers. So in molecular iridium dimers, you have these cyclic groups around the iridium, and that really impedes this interaction between adjacent iridium groups, right? So here, while we can think for the electrodeposited oxide, you can access these long-range interaction between these oxo species. That's going to be significantly lesser when you have these isolated iridium dimers. So I won't go into the details, but you can either look at that publication there, or just trust what I say when I say that we have similar optical spectra for both the heterogeneous and the molecular catalyst, and we can go in and fit these three different redox transitions. We see that the redox transitions are shifted slightly to more positive potentials in the case of the molecular catalyst, and this is essentially just because of this ligand effect of these pyridine centers that are directly bonded to the metal iridium center. But essentially, you still have these same three redox transitions, particularly the one that forms at high potentials that we've been measuring the kinetics for. And what's really interesting now is that if you see this molecular iridium center and measure its rate of decay as you increase the potential, these squiggly things are just the noise of the instrument. But by and large, you're increasing the potential quite significantly, and you're increasing the density of these oxidized iridium centers quite significantly. But that doesn't have a very strong effect on the rate of the decay of these species, or on the rate of catalysis when you're specifically looking at those open circuit decay measurements. So as a summary plot, if we compare this decay time constant of the molecular catalyst compared to these heterogeneous iridium centers, we see that this is pretty much constant in the case of the molecular catalyst, whereas in the case of the heterogeneous catalyst, you have this reaction becoming more and more faster as you increase the potential, which essentially increases the coverage of these species. But the minute you can't get this cooperative interaction between these oxidized states, that the actual rate of reaction stays the same, and the catalysis for these molecular centers is essentially driven by just having more oxidized species on the surface, but each oxidized species essentially has the same rate of the reaction. So we can essentially put that information all together, where we can see that at low potentials, the molecular catalyst is in fact has faster kinetics, and that's because of this stabilization of the d orbitals in iridium by the pyridine pi orbitals, which puts it slightly weaker binding of these oxo species and to a more optimal position compared to iridium oxide. But it's really as at higher potentials and under more applicable reaction conditions, while this heterogeneous iridium oxide can access these cooperative interactions, the molecular iridium centers cannot, and that really makes the heterogeneous catalyst a much better catalyst under these conditions. So with that, I've hopefully convinced you about the importance of studying reaction kinetics, and in this case specifically oxygen evolution kinetics, and using operando techniques. And today I've shown you an example of one lab scale technique that we can use to try and understand what really drives the catalysis on some of these different really interesting materials, and how we can start thinking about relating the density of the species that we form to the catalysis of the reaction, and start. Well, we're very much at just the surface of trying to understand how these cooperative interaction between these different species is governing the catalysis, and what in fact can we do to start really tuning these long range interactions to improve catalysis. So with that, I'd like to thank all the different people who've contributed to this work, as well as the funding bodies that have made this work possible. And I would also then like to thank you for your attention, and would be happy to take any questions.
Thank you very much, Reshma. So we have a panel discussion at the end where the questions will follow. So I'm already looking forward to that. And now I will share my screen again to introduce the next speaker. So the next speaker is Paula Sebastian Pascua from Copenhagen. So originally she's from Spain, I believe, but she now works in Copenhagen, and she's starting up her group. She recently got a nice investigator grant for young scientists from the Danish government to start her own group, and she focuses on how electrochemical techniques and other characterization techniques can be used to understand what the surface of our electrocatalyst material looks like. So, Paula, if you're ready,
yes,
I give you the floor.
Yeah, I will share my screen. Yes, I hope. Sorry, I wanted to start at the beginning. Yes. All right, now I'm ready. I hope everybody can hear me well and can see the screen. And Bart, thank you for the introduction. Before starting this talk, I want to thank the organization, because it's for me for this invitation, because for me it's a pleasure to have this opportunity to share my research. It's basically focused on electrochemical characterization of copper catalysts. So just before starting this talk, I would like to do a very brief introduction of what I have been doing. So I'm originally from Spain, In November 2018, I moved to the University of Copenhagen to do a postdoc research with Professor Maria Escudero-Escribano as my mentor. And recently, in November 2022, I became assistant professor, and I also got a Billund Young Investigator grant to start to build my research group. So basically, my research is divided in two main topics. So on one side, I investigate the electrochemical behavior and the interfacial properties of different copper catalysts, but also copper single crystalline electrodes, because copper is a very good and interesting material for different electrocatalytic reactions. But on the other side, I'm also very interested in the preparation of bimetallic nanostructures using electrodeposition technique and green solvents like lipotectic solvents. But today I will focus more on the research I have been doing with copper single crystals and other copper surfaces. So just to put the things in context, it's clear that today there is an urgent need to replace fossil fuels by clean energy sources, and the way that electrochemistry can contribute to this transition to a decarbonized industry is through energy conversion devices like an electrolyzer that use clean electricity to convert molecules that exist in nature, like carbon dioxide, water, into chemicals and fuels that can be also used in a fuel cell to produce clean electricity. But all these conversion reactions, conversion of molecules, they occur on the surface of electrodes that are in contact with electrolyte. And this region is called the electrifying interface. So if we want to catalyze these reactions more efficiently, it's clear that we need to design more stable, active, and selective electrifying interfaces. And to get this goal, we need to answer a few fundamental questions. And one of these fundamental questions is which surface active size and both composition and structure facilitate these reactions. And once we know this answer, it's easy to go and try to tailor and prepare multimetallic nanostructures that can make these processes. So why I have been investigating copper-based electrocatalysis? So I really think that copper is a key material for this energy transition, because copper is a very good catalyst for different reactions, not only for the conversion of carbon dioxide to fuels and chemicals, but it can be also a good material for the oxidation of biomass molecules like phosphorus oxidation, or also copper combined with other metals can be used for the reduction of nitrate to ammonia, nitrogen for water remediation. But we know that electrocatalysis is structure sensitive. Electrocatalysis, both the product distribution and the activity, is going to depend on the surface sensor, and more specifically on the active site geometry. And that's what motivates me to investigate copper single crystalline electrodes or well-defined surfaces, because copper single crystalline electrodes, they are surfaces that are atomically well ordered, and this means that the active site positions, the geometry is very well defined, and the difference between the different single sets is that the way that the atoms are organized is different, and the coordination number or the number of neighbor atoms is different. And this type of studies with single crystals, actually, they can give us a lot of valuable information about how the interactions between the electrolyte and the surface structure can affect not only reactions, but also different processes that occur on the electrified interface. So, actually, the research I have been doing in the last year is quite fundamental. We just wanted to cover some aspects and questions related with the copper electrolyte interface structure. So we started investigating with this the blank cyclic voltammetry or the voltammetric fingerprint of the different copper single facets, because this voltammetric fingerprint that I will show later, they will give us from the voltammetric fingerprint, we know if we are working with clean and ordered surfaces. And now once we can reproduce the voltammetric fingerprint, we can go to the next step, in which we can try to find information about important interfacial properties, experimentally try to determine these properties, like, for example, the potential of zero charge of the copper electrolyte interface, and I will go to this later. Then we want to investigate also how the interactions between electrolyte and surface, specifically how an ion of the electrolyte, an ion absorption, these sources can affect some important processes like this carbon monoxide absorption of copper, because carbon monoxide is a key intermediate in the CO2 reduction of copper. Of course, the surfaces they are very dynamic, and they can change depending on the potential limit conditions or the potential window of that we are using in a specific experiment. So we wanted to analyze if how the copper electrolyte interface structure can change depending on different potential conditions, and we could obtain information about that just using electrochemical techniques. And lately, at the end, the information you can get from single crystal electrodes is nice from a fundamental perspective, but single crystalline electrodes, they are not scalable. So we want to move to more realistic catalysts like nanostructures. But we can use the information of the single crystal electrodes to try to understand more the surface structure of copper nanostructures. And for that, we need to be able to quantify the amount of different active size geometries on nanostructures. And this is something we are working on. So let's say this is more or less all the points of this talk. So we will start with the first point, that is about the voltammetric fingerprint. So I just want to introduce the type of experiments I do, which are very, very simple, and I think most of the labs that work will do the same. So single crystalline electrodes, they to be able to do electrochemistry, and then they require a special surface treatment, or they require a surface treatment to be sure that they are ordered and clean. In this case, to work with copper single crystal electrodes, I use the most classical technique, that is electropolising. So basically, I'm oxidizing the surface in an electrolyte that is contains mainly phosphoric acid, because the phosphoric acid is going to have a labeling defect, and then I will get a flat relative order surface. And then I do the electrochemistry in a conventional or a classical 3-electrode cell, in which my working electrode, the single crystal, is in the hanging meniscus configuration. And this configuration is just to be sure that only the single facet is in contact with the electrolyte, but not the size of the electrodes, which are polycrystalline, because at the end, I just want to get the information of the single facet. And then, of course, depending on if I'm working in acid neutral pH or in alkaline media, I use a perfluoro of gas, and this can contaminate the surface. So single crystalline electrodes are very sensitive to contamination, and unfortunately, if there is contamination, the contamination is also reproducible on CVs. So before starting to record or to investigate the voltammetric fingerprint of copper 111 and copper 100 single crystals, so I checked the literature, and in 2020, this group of people, they published this very nice paper in which they published several papers, and they report that the voltammetric fingerprint of copper 111 and copper 100. So here you can see what is a voltammetric fingerprint. So voltammetric fingerprint is just a blank CV that has which shape, intensity, and position with the potential is very different for each single facet. And this allows us to differentiate different single facets. In this paper, they did the characterization also with STM, in which you can see that they have a surface that looks quite ordered even after electrochemistry. But they were using as a surface pretreatment ultra high vacuum technique and sputtering and annealing. And this is something we didn't have in our lab. We were using the classical method of electropolising. So the first step was to prove that actually we could reproduce these cyclic voltammetries just by using electropolising. And actually, it was possible to reproduce this CV. They using electropolising technique, they look quite similar to the one reported using ultraviolet vacuum conditions, just that, of course, electropolising is a little bit more aggressive treatment. You can have some defects that you can see in the CV. For example, on copper 1, here there are a few defects. On copper 1, here there are a few defects. But the features, the intensity of the features is indicating that our surfaces are mainly 111 in this case, or 100 in this case. So at that point, we were ready. We were sure that our methods were good to reproduce the voltammetric fingerprint. We were ready to move to the next step. That was try to get that of information about the copper electrolyte interface structure. And for that, we wanted to investigate and determine the potential of zero charge of this of the interface. And why? So the potential of zero charge is actually a very important interfacial property in electrochemistry. Is the potential at which the charge on the surface, the free charge, is zero. So it gives us the relation between the potential scale we use, the reference electron, and the charge distribution on the surface. And actually, this value is related with the work function of the metal, but in this case modified by the interaction of the electrolyte. However, we have a problem experimentally, and is that the finding or determining this potential of zero charge is not easy, because it's very difficult experimentally to decouple the free charge on the surface from the total charge that also contains Faraday contribution. And these Faraday contributions can come, that, for example, because of a specific absorption of anions that they contribute with charge. So in order to be able to decouple the free charge from the total charge, during my postdoc research, I went to the University of Alicante, where actually I did my PhD to work again with Professor Juan Feliu and Victor Climent, because they have in Alicante a very nice technique that is called laser-induced temperature jump technique, that is used to estimate this potential of zero charge. So in this technique, basically, we just apply a laser pulse on the copper and the metal electrolyte interface, and this laser pulse causes a sudden increase of the temperature of the interface that change the change the electrode potential, and basically we are just measuring the change in the change in the electrode potential with when the temperature relaxes. So it's a very fast thermal perturbation. We measure the change in the electrode potential when the temperature is relaxing. And this change in the electrode potential is mainly due to a change in the dipolar contribution to the potential of the electrode, because we are in aqueous solution, water molecules, they are dipole, they orientate with the electric field on the surface, so they contribute to the electrode potential. So when we apply when we increase the temperature of the interface, we induce disorder in the water solvent network, and this changes the electrode potential. So if we are at a potential that is higher than the potential of zero charge, and the charge on the surface is positive, we have a dipolar negative contribution, and in this experiment we obtain a positive transient. On the other side, we are at a potential that is more negative than the potential of zero charge. The dipolar contribution is positive, and we obtain a negative transient. And if we are in a potential in which close to the potential of zero charge or the potential of zero charge, there is not electric field on the surface, the water molecules are randomly distributed at a transient that is close to 0, 0. And here is this is how this experiment typically looks when here I'm just showing the laser transients of the copper 111. As you can see, at sufficiently high positive potentials, we have positive transients, but they start to decrease in intensity as the potential of the electrode is decreasing until they change signs, because we are changing surface polarization. And we can use this data, this in the transients, to calculate the thermal coefficients. And this using this this thermal coefficient, it's possible to find at which potential there is this change in sign of the transients, and at which potential there is approximately the potential of 0 chairs of the copper electrolyte interface. And we did this for both copper 100 and copper 111 single phases. So what we found is two important results, at least in my opinion, is like first, the potential of 0 chairs of copper 111 is higher than the potential of 0 chairs of the copper 100, and the difference between these two potential of 0 chairs value, it's similar to the difference or close to the difference between work functions, which makes sense because at the end, copper 111 is a more close, has a more close packet structure compared to copper 100. But in addition to that, it's very interesting to see that if we look at the Planck Society voltammetries, in any case, the potential of 0 charge or is close to this feature here and this feature here. So this feature here is reported as the absorption-dissorption of hydroxide or OH on copper 111 and the absorption-dissorption of OH ions on copper 100. So from my perspective, this is telling us that or the charge distribution on the surface is affecting how the anions are distributed on the surface. Also, that the interaction of the electrolyte and the anion absorption is influencing these interfacial parameters, that is the potential of 0 charge. So they are kind of related. So all right, after doing this type of experiment, we wanted to get more information about the copper electrolyte interface structure. But in this case, we investigated the copper phosphate solution electrified interface, because with the phosphate biphase solution, we can investigate a wider pH range. So then we can also get information about how the pH is affecting the structure of the electrified interface. And after that, we wanted also to try to understand how the methyl electrolyte interface structure can affect the absorption of CO, of carbon monoxide on copper, because as I said before, carbon monoxide is a key intermediate in the CO2 reduction on copper. So here in this plot, you can see the red line corresponds to the Planck series of copper 100 and copper 111 in contact with a phosphate buffer solution in alkaline media. And similar to the sodium dioxide electrolyte, we also have like these nice features, these peaks here, this pair of peaks that corresponds to the anion absorption dissorption of copper. If we plot the potential of this anion peak with the pH, we find that the difference between the potential of the anion peaks is similar to the difference in potential with the potential of 0 charge of copper 101. Copper is absorption strength of the anions, or the energetics of this anion absorption dissorption cannot be activated by work functions of the metal. But then if we move to the situation in which the solution is saturated with carbon monoxide, what we see is that the cyclic voltammetry, now the black line, is a little bit because the peaks are shifted to a little bit less negative potential values. So what is happening here is that the carbon monoxide, which absorbs quickly on the surface, is absorbing on the surface at the potential in which the anion is about to dissolve. So it means that the carbon monoxide cannot be absorbed on the surface unless the anion is able to be dissolved. So the anion is controlling The anion is controlling the absorption of CO, and it's also controlling the potential at which the CO is going to be absorbed from copper, which is going to affect also the onset potential for CO reduction. In the case of copper 100, this CO absorbs a little bit earlier because the CO absorption seems to be a bit stronger than copper 111, but it's still controlled by anion desorption. So, all right, here is the conclusion is anion is controlling the absorption of CO. But we see that there is a pH dependence on the CO absorption. And this it means that the CO absorption shifts to slightly more negative potentials where we are increasing the pH. And this pH dependence is even stronger in acid neutral media. So this pH dependence cannot be explained by differences in potential of zero chairs because potential of zero chairs is not relative, it's not dependent on pH. But the absorption of the species, these species that are absorbed, they depend on the pH. So to try to explain what's going on, our collaborators in the group of theory in the University of Copenhagen, Alexander Bagger and Amanda Petersen from Jan Rosmeiser's group, they made simulations of the copper electrolyte interface structure. And at the end, to understand this pH dependent, we have to see at the elementary reaction that is happening in the surface. So it's like the elementary reaction is carbon monoxide is replacing the phosphate species on the surface, and this reaction has the transfer of protons and electrons. A specific number of protons and electrons are transferred, and this number of electrons and protons that are transferred is what determines the pH dependence. And then if we see at the results, to understand this, we conclude that the species that are absorbed on the surface, even at pH that is acid or neutral, they are or phosphate or monoprotonated phosphate species, which these species you find them in the even at acid pH, despite that you don't expect this at this pH. But this is indicating that the acid-base properties at the interface are different than in bulk solution. So here we have another important interface property that is not only the potential of zero chair, it's also the surface pK that can be affected by charge distribution on the surface. So basically, the conclusion of this is like the copper electrolyte the methyl electrolyte interface structure is controlling the potential window that we need to absorb CO on the surface at different pH, and this can affect the onset potential for the CO reduction copper. But of course, we were only investigating a very narrow potential window in which the blunt CVX looks quite stable. So it means that I would expect that the interface is not really changing so much. But actually, it can happen that during reactions the surface is changing, and this is something that we can already see just by using cyclic voltammetry. Because if with the cyclic voltammetries, both without CO and CO in solution, as soon as we increase the potential limit to more negative values, what we see is that these features in the cathodic scan, they are completely shifted to more positive values. So it's clear that something is happening, maybe a change on the surface structure or it's just a change on the copper electrolyte interface. But what is interesting here, from my opinion, is that this type of changes we see in the cyclic voltammetry, they are depending on the potential. So it means that as soon as I change the potential limit conditions, I will obtain always the same CV. So in this narrow potential window, I always obtain this CV. Then if I go to more negative potential window, then something is happening and the feature is displaced. But then if I switch again to this short potential window, I recover the feature. So all these changes seems to be reversible with potential window. And I think this is something that is important to investigate and to understand, because maybe we can control this type of changes just by applying potential. And this is something that we continue investigating. So until now, I just presented some. I just thought that by using just cyclic voltammetry, very simple electrochemical experiments, you can get a lot of information regarding the copper electrolyte interface structure. But this is possible because single crystal electrodes, they have nice features that makes different single phases different. But if we move to copper polycrystalline electrodes, then it's different because on copper polycrystalline multifaceted surface, you cannot get so much information from cyclic voltammetry, basically because these features are very small. So you cannot get quantitative information about surface structure on polycrystalline surfaces just by looking at the cyclic voltammetry. So at this point, I was thinking, what can I do to quantify the surface structure, to quantify the active size on copper of different geometry? Typically in electrochemistry, one classical technique is using methyl and the potential deposition, where you reversible absorb and dissolve of a monolayer of a methyl on the surface, and this provides a cyclic voltammetry that has intense and very sharp peaks. And when I was reading the literature, I found that around in the 95, Broussard reported the lead under potential deposition on copper 111 with and without chloride. And with chloride, it's surprising because you obtain a nice CV that has very sharp peaks, very intense and very sharp peaks. And I thought maybe with this technique I can decouple facets. So then, this is a work that was done by Pedro Mazaira Couce, that at that point was a student of art. So we did this research and we report the LUPD on the copper single basal planes, and you can see that the different single facets they have very intense peaks, but they are very well separated in the potential window. So I thought, wow, maybe we can use this to differentiate facets in polycrystalline surfaces. So we did the first experiment was to do the polycrystalline copper electrode, which has several peaks and one intense peak that is it overlaps with the 111. You can try to decouple these peaks, and then we found that this peak, the polycrystalline has about 60% of copper 111. But then in the next experiment, we thought, okay, now we are going to change the surface structure of a copper polycrystalline electrode, but just using a very classical method that is oxidizing and reducing in sodium chloride. And we did that, and it's clear that you see a change on the surface structure by using a scanning electron microscopy, by SEM, but then you can also see this change in the LUPD. So yeah, the LUPD is very sensitive to the surface structure. You see different distribution of peaks, so it means you are really changing the facet contribution on the surface, and you can measure it. And you can also measure the electroactive surface area by just integrating the charge on the surface. And the last experiment, and with this I'm going to end, is like, I wonder, is it possible to use this technique to tune in a rational way the facet distribution on copper, to try to change the distribution of facets, but in a way that I want. And actually, I think so, if we can quantitatively measure the change. And I think this is something that I think this technique has the power to do that. It's like if I can change the surface structure and I can do it in a way that I can differentiate the different facet contributions. And I hope in the future I can present more about this work. And with this, I just make an overview of all this research with copper and how just by using cyclic voltammetry you can get a lot of information. And before finishing, I just want to say thank you to all the people in the University of Copenhagen, especially my mentor, Professor Maria Escudero-Escribano, also the people at the University of Alicante, our collaborators in DTU and in TOPSO, and different funding agencies and my colleagues at the University of Alicante, and to you to listen to me. And thank you very much.
Thank you very much, Paula, for this wonderful talk. The same holds for you. So the questions we have to save up for the panel discussion at the end. So also for the audience, please post them in the chat, and then we can cover them in the panel discussion afterwards. Thank you, Paula, and let me now introduce the next speaker, which is going to be Mariana Monteiro, and I know her for several years. We just met last week or 2 weeks ago for the first time in person. So I'm also happy to have her in this session. So she worked in Leiden. She did her PhD there and graduated in 2022. And after that, she went to Germany, to Berlin, where she now is leading the electrode electrolyte interfaces research group. So really close to her heart is this topic of this session today. And we look forward to your talk. And if you're ready, you can start sharing your screen.
Yes, thank you, Vard. I hope this gives me an okay that everything's fine.
Yes.
Okay, very good. So, hello, and thank you, Vard, not only for the introduction, but also for the invitation to join this very interesting seminar series together with Paula and with Reshma. And I hope in the coming 30 minutes to talk to you about cation effects on the hydrogen evolution reaction, and to convince you that they are not always the good guys, but that depending on the conditions you are working and on the species that you have, they can either promote or really hinder a reaction. Just before I start, so currently I'm a group leader at the Fritz Haber Institute, leading the group on electrode electrolyte interfaces, which I just now realized that it's a very similar name to the title of the seminar. So I'm glad to join you here. So first of all, Reshma already helped me out here, so I can save some time. And she introduced to you hydrogen being produced on the cathode and water being produced and water being oxidized to produce oxygen on the anode, and that's shown here in a very simplistic view. And while Reshma's work focused on the anode, which is normally the bottleneck for this reaction, it is still very important also to understand what's going on the cathode. And I will argue with you that that's not only important for this reaction itself, but also because this reaction competes with many other electrocatalytic reactions that take place also at negative potentials. I'm especially interested, if we zoom in here on what's happening in the catalyst surface, on how, for instance, different ions interact with the surface and with the reaction. And the reason why is because depending on the hydration structure of these ions, they can lead to different, for instance, capacitances at the interface. The solution resistance behavior can be different, and so on. And like I told you, the focus of my talk it's on on the cathode side, so on the hydrogen evolution reaction. However, you can think that if you are doing CO2 reduction or nitrogen reduction, nitrate reduction to ammonia, for all these reactions, if you do them in aqueous media, hydrogen evolution will always be there as a parasitic reaction. So independent of what you are working on, I would like to ask you to generalize my talk a little bit and think that you can always think about it in terms of like, how does this then compete with whatever other reaction is happening? So what I'm basically interested in trying to define is how, what actually defines how cations interact with these reactions, and not only how they impact the activity. So if we think about hydrogen evolution, if we do it at acidic pH, what is reacting is actually hydronium ions to form hydrogen. Now, if we move to neutral or alkaline media, the reactant is actually water. And one can think now, if we introduce different ions in the electrolyte, which you can think not only about like that your starting electrolyte contains these ions, but in large-scale electrolyzers, you will always have some degree of contamination in your water adduct. So you can always think about this in terms of like, if one of these species is a contaminant, how would that then impact the reaction? So to try to define what cation property is important for these effects, I give you here, for example, different species, and throughout my talk, I will argue with you that cation acidity is actually a very appropriate descriptor for the effects we observe. And what is cation acidity then? So it's nothing less than just, let's say, this is just textbook data. Here I'm plotting for you the hydration energy of a cation, so how strong water interacts with this ion, as a function of the square root of the charge over the radius. So this is just basically a relationship of how strong water feels the charge and interacts with this positive ion. And you can see that for the species we looked at, you go from very, let's say, positive hydration energies until very acidic ions, for example, like aluminium, that is very small and has a very large hydration sphere and very, very negative absorption, Gibbs free energy of hydration. So first of all, we are going to focus on the hydronium reduction reaction. And the way to do that, Paula also already nicely introduced a very nice, simple, let's say, electrochemical cells and how with voltammetry we can get a lot of information. Voltammetry experiments that were done primarily on gold, and the catalyst for the improvements or changes in the rate, it's good to start with something that is bad and try to make it better by engineering the electrolyte. So for all the experiments you will see here, I was using a background electrolyte that was composed of lithium sulfate. And basically what that does is that, so all the effects you will see are just due to 1 millimolar of these foreign ions added to a lithium background. So these are the cyclic voltammograms we obtain. You see here the current as a function of potential. If we add 1 millimolar of all these different species, solution does not really affect hydronium reduction a lot, because supposedly the dissociation of hydronium molecule to donate a proton to them to see, and that is interesting, is that different peaks appear in the voltammetry. And they for these peaks, it's basically the fact that once you do your voltammogram increases and reaches basically the pKa of hydrolysis of these different ions. And then you also see that aluminium has a lower pKa of hydrolysis than, for example, neodymium and cerium, and that's why you see here this peak first. And this is basically due to hydrolysis of these ions. There is a discharge of protons at the interface, leading to sort of like a second proton or hydronium reduction regime. The trend is just not followed by beryllium, and the reason for that is because beryllium also forms complexes with sulfate, and that sort of changes its solution chemistry a little bit. Now, our collaborators in Tarragona, so specifically here Federico Dattila, ran DFT and molecular dynamics simulations using a gold surface with different ions and water molecules. And first, we basically just looked at the Gibbs free energy for hydronium dissociation. And you see here snapshots of two different states of the simulation. And now if I plot for you the Gibbs free energy as a function of cation acidity for the different ions that we were studying, you can see, first of all, that water dissociation in general by the negative values here, like I told you before, it's indeed a very favorable process, that there is a very low barrier for that. And even though there is a trend as a function of cation, it makes sense why in the experiment we actually almost don't see an effect. And it's the same also if we look at the energy for an absorbed hydrogen molecule on the surface, and basically having a cation in the vicinity for gold at least almost does not change that, which nicely agrees with the trends we saw in the voltammetry. Now, if we move from acidic pH to neutral and more alkaline pH, and then we will start now looking at water reduction, we can first, also based on the voltammetry, look on the activity that we get if we have these different ions in solution. And you'll see here the water reduction activity, again plotted as a function of cation acidity. And directly you can see some trends. So first of all, that if you are within one valence group, the less acidic cations actually lead to higher activity. And if you compare the different valent groups, you see that 3+ species lead to almost a 20-fold increase in activity compared, for example, cesium and lithium. And surprisingly, neodymium is actually one of the best performing ions. Similar trends we can actually find if we look at the potential in which the activity actually starts to increase. So you see that here on the y-axis, again plotted as a function of cation acidity. And you see that within a valence group, you have quite a nice trend in which the over potential, let's say, for this reaction is always lower if you are with the least acidic species. And it's even much lower, so a factor of 400 millivolts lower if you are using 3+ species in the electrolyte. Again, we try to elucidate that better with DFT and molecular dynamics simulations. And here you see again the same kind of gold slab, but now with just looking at the water molecule that is inserted in the vicinity of the different cations. And first of all, what you see is the activation energy for the water dissociation. And contrary to the hydronium, you see that now it's not really a favorable step that's actually on gold, believed to be the rate determining step for the for evolving hydrogen. And you also see that the barrier is much lower if you have acidic cations like aluminium. And in comparison, for example, with the very non-acidic cesium. However, here now, if we look at our activity, the activity is actually higher in the presence of neodymium, but based on the activation energy plot, we would actually expect a higher activity in the presence of aluminium. So to try to understand that further, we also calculated the driving force for different ions to accumulate at the surface. Because it's not only important what that does to the reaction, but actually how much of that ion you have near the surface. And if we look at that then, which is the plot here on the left, so on the y-axis is basically a quantity for the driving force of ions to accumulate as a function of cation acidity. And we see that actually the non-acidic cations are at much larger quantities at the interface than their acidic counterparts. So that sort of helps us to understand why neodymium is actually the best performing ion for water reduction. And it's basically because even though aluminium is the most acidic one, neodymium is in much larger quantities at the interface. So there has to be a balance between acidity to make water very reactive and accumulation at the interface. So it doesn't matter if you have something that makes the reaction very active if that is not existing at the interface in large quantities. And neodymium sort of like is a very good compromise between the two things. So now just a partial summary. One thing we need to keep in mind when thinking about activity and the effect of ions, it's accumulation at the interface, and that we saw that weakly hydrated cations, so less acidic cations, accumulate more near the surface than their acidic counterparts. In the sense of hydronium reduction, we see very minor effects, and we also see, based on simulations, that hydronium dissociation to donate a proton to make hydrogen is a very fast reaction. It's almost barrierless. And also that, interestingly, that if you have acidic cations, due to hydrolysis, they discharge protons at the interface once the local pH changes. Now, for water reduction, I also hope that I now showed you that you have to have a compromise between cation acidity and its tendency to accumulate at the interface. So very acidic and weakly hydrated cations, like neodymium, are sort of like the best compromise between the two things. Moving on now, so we looked at acidic and neutral to alkaline pH, and now I would like to take you to real alkaline hydrogen evolution, which is basically the cathode reaction happening in electrolyzers like the ones Reshma showed you in the beginning of her talk. And I bring you for here a commercial device, so for example from Nel Hydrogen. And we know that it's sort of accepted that in these devices, the electrodes used at the cathode are nickel and carbon immobilized on platinum. And the electrolyte that it's used, it's very concentrated potassium hydroxide. And I hope to now, in the coming slides, and now I think comes the part of like the villains of my talk, that even though this electrolyte is very conductive and it's the choice in the industry, perhaps it's not the most ideal for this reaction. So the way I'm hoping to convince you of that is by looking at the activity of hydrogen evolution as a function of cation concentration. And with that, we make this reaction order plots. So if we do hydrogen evolution on platinum, which is the catalyst here used in the electrolyzer I showed you, and we start increasing the concentration of lithium, which you see here in the x-axis in the electrolyte, you see a positive reaction order. So this positive slope basically means that this is promoting the reaction. And this was done at pH 11, so a much less alkaline pH than what is actually used industrially. And now, surprisingly, if we do this in potassium hydroxide instead and increase the concentration of potassium, you see that actually the activity goes down significantly. And this is even more pronounced if you increase the pH further. So imagine in 25% potassium hydroxide then. Now, interestingly, if you do this on gold, first lithium at pH 11, you see again a promotion of the reaction. The activity goes up if you increase the cation concentration. However, if you change to potassium on gold, increasing the potassium concentration still promotes the reaction. And on gold, you actually need to go up to pH 13 to start seeing that this becomes detrimental to the activity. So to try to summarize all that, what we see is actually, so if we plot the HER activity as a function of the local cation concentration or the local pH, you could call it one of the two, we see that for both lithium and potassium, there is initially a promotion regime if you start increasing the concentration of these ions in the electrolyte. However, at high cation concentrations or high pH, if you have a weakly hydrated ion like potassium or cesium, your activity actually starts to go down. And basically, gold and platinum are both show this phenomena. However, it seems that platinum already only exists here at this inhibition regime. So this would suggest that actually cations interact much stronger with platinum than they do with gold. However, I must say that still the reason for this hindrance of the reaction, it is still unclear to us, and I would be happy also to discuss about it during the discussion session afterwards. Now, even though we have all these nice insights about the electrochemical interface and how ions interact with a reaction, the reality is that we don't really know how the interface looks like. So always, like I've done this also, we draw sort of like cartoons, right? We put molecules where we think they are, but the reality is that we don't really have enough numbers to make these cartoons more realistic. And the solution for that, it's up around the characterization, and it's something that we are heavily focusing on my group at the moment. And the way we do that is using surface X-ray diffraction. So you see here the diffractometer at the P23 beamline here in Hamburg in Germany. And I will just quickly in one slide try to motivate why this is a strong technique to look at these ion layers. And basically, if you have a crystal, an infinite crystal, and you look at the scattering intensity as a function of reciprocal lattice units, you get Bragg peaks. I think all of you probably have heard of Bragg law. Now, if we truncate this crystal, so we create a surface, you get what we call crystal truncation rods due to this surface. And here at the bottom, you can also see a representation of that in 3D. Now, if on top of the surface we add, let's say, a layer of cations or a layer of water, this will lead to very specific changes here in these anti-Bragg positions. And we can look at that specifically looking at the 00L rod, which tells us the out of plane order. So we are not sensitive to anything in the XY position, so H and K, but only out of plane, so only in the Z position if you go outward of the surface. And again, another disclaimer, it's important to remember that this is a diffraction technique. So we are only sensitive to ordered layers. So anything that has some degree of disorder or represents something amorphous, we will not see a signal from. So we did these measurements using a gold 100 electrode and looking at how it interacts with cesium. And basically here on the right side, you see the data we obtained at pH 13 and also at pH 3 to try to start understanding a bit what happens that these weakly hydrated ions interact so much stronger at high pH. And if we now, I don't expect you to directly understand this data as a function of potential, but if we now use a very simplistic model to try to fit this data that just contains the gold layers and an ordered cesium layer in the vicinity of the surface, you can see that we get very good fits for it. And now from these fits parameters, we can extract a few important and valuable quantities. The first of them being what is the distance between the cesium ions and the surface at the different pH and the different potentials. And in red here, you see that at pH 13, as we go to more negative potentials, the cesium cations move close to the surface. And the same happens at pH 3. However, if we would now, let's say, shift these curves by to plot this versus the pH independent scale, you would see that still intrinsically at pH 13, at a given potential, so let's say Paula talked a lot about the potential of zero charge, and this is telling you that if we are at the same distance from the potential of zero charge, which would mean the same driving force for ions to go close to the surface, is still at pH 13 for some reason, cations sit closer to the surface than in acidic pH. Now we can do the same, and instead of looking at the distance, we can look at the occupancy, so the coverage of ions on the surface. And again, we see that if we go to more negative potentials, the occupancy, or you can call it the coverage of ions, increases, and it's also higher at pH 13. However, you also see here that the arrow bars on the occupancy are very large, and that basically tells us that there is a very large uncertainty on the occupancy, so suggesting that these are very disordered layers. However, on the distance, we have a very good precision. So still, this does not explain why hydrogen evolution starts to be hindered at pH 13 and above in the presence of these ions, because if you look at this distance here, you could still in principle fit a water molecule here in between. So even though these are valuable insights, we should still look further into that. So in summary, I hope I convinced you that cations are important and that they can either promote or significantly hinder reactions, and that happens differently if you look at hydronium reduction, so hydrogen evolution in acidic pH or in neutral to alkaline. And that it's very important to always think about not only activity, but the concentration of these ions near the surface. And that I think now we are confident, especially with the surface XRD data, that weakly hydrated ions accumulate much more at the interface. And that I hope you can translate these insights also for other reactions happening in aqueous media at cathodic potentials. And also that we see that in strongly alkaline media or very high cation concentrations, if you use weakly hydrated ions, they start hindering HER both on platinum and on gold. But it seems that on platinum, this is much more pronounced already at low pH. And finally, that with operando surface X-ray diffraction, we are now moving towards actually putting some numbers to search cartoons and fully characterizing the ordered layers in the electrochemical interface. So finally, I would like to thank my previous collaborators, so especially Professor Mark Koper, where I did my PhD at Leiden University, Nuria Lopez and Federico Dattila that read the molecular dynamics and DFT simulations, and also Andreas Stille and Leon Jakob at the synchrotron in Hamburg for the collaboration on the surface XRD measurements. With that, I would also like to thank our department here at the Fritz Haber Institute and my group on electrode electrolyte interfaces. You see here our first members, and also you might find interesting that we still have a few positions open. So if any of what I told you now interests you, please feel free to send me an email. So I leave you with the summary, and thank you very much.
Thank you very much, Mariana, for the wonderful talk. And now I think we can invite the other speakers as well. And we can start the panel discussion. So let's see. This is ready. Okay, I think we can start, right? Okay, so there was one question already from the audience, and I want to start with that, and it was for Reshma from Shihong. So thanks for your wonderful talk. And as you said, the coverage is the key for the reaction. How to make it in a large scale? Can you comment on that?
So how to have a larger coverage? Is that the question?
How to have a large coverage if you want to do these reactions on a large scale? I think that's the question. So,
well, I guess the first part of the question, so we have been doing also measurements in actual kind of electrolyzer setups where we also see the coverage is an important parameter. So this idea that coverage is important kind of translates along the scale of being lab scale to a more practical scale. How to tune the coverage is a more tricky, interesting question. So one way is obviously tuning the catalyst and changing the binding properties of it. A more, I guess, interesting way is to use some of what Mariana has been saying with tuning, for example, the electrolyte that can indirectly stabilize different intermediates. So we've been looking at some of electrolyte effects too for the oxygen side and seeing if you had certain ions at the interface, for example, they could almost facilitate long-range order. And with that great kind of last bit of what Mariana said, where if you look with surface diffraction, you can see there's some ordering at interfaces. And you could almost imagine a really beautiful hydrogen-bonded network that can be mediated by ions. And all of this is challenging to measure and even more challenging to tune. But I think this is the open question and why we continue doing what we do, I guess.
I guess so too. Yeah. So this already creates the bridge to Mariana's talk, which also showed this huge effect of the cation. So do you want to comment on that, Mariana? You want to
Yes, sure. And no, it's more a question back to Reshma, because it's indeed I find interesting that with on the oxygen, on the anode side, these effects are also there. But do you think, Reshma, that it's possible to sort of like differentiate what are like, because with these layered materials like you showed, you also can have ion intercalation. And that to me, it's sort of like different than just an ion sitting on top of the surface, sort of like in this distance of 3 point something. Do you think we can somehow differentiate like the effect of ion intercalation with the intrinsic ion effect on the interface?
No, I think that's really hard. I'm not sure if we can, and you're right. For most of when we are trying to study ion interactions, we look at very crystalline surfaces and not really these 2D materials with have channels. So we look at metal oxides that are perfectly crystalline, and we've done a bit of work on single crystals too. But yeah, I think the interface becomes very, very complex if you have the possibility of ion intercalation and ions absorbing at the surface, and where these ions would be, I guess, exponentially a harder problem, an interesting problem, but exponentially harder, I think.
Yeah. I do find that it's beautiful that we see these effects as such positive potentials also during OER, because I think until a few years ago, we tend to think that cations only strongly interact when the net surface charge is negative. And always when I give this talk, I see some students sometimes saying, but you still find an ordered cation layer at very positive potentials. And
yeah, I think that's because metal oxides. So with high potentials, I guess where metal oxides, not metals, and metal oxides are own have a life of their own almost, right? And then what the oxo can have a charge slightly 1- or so, and how these bonds are between the metal and oxygen, and where the charge is sitting, and how that determines the ion ordering. I think this is interesting. But yeah, you're right. We see it at positive potentials, and it's partly confusing, but also partly you can justify it more from an intuition point of view. But yeah, I think we're miles away from obviously the beautiful picture that you have for metals, which is also, there's a lot of work to do on metals, and I think metal oxides is even playing a bigger catch-up game with metals, right? So
definitely.
Great. So to now create the bridge to Paula. So you showed your wonderful voltammetry technique also to quantify surfaces and roughness. So how do you think this all connects, and what is the potential for different characterization techniques to try to understand this? So we have seen many different aspects of characterization of these interfaces. Okay.
So, for example, something I was thinking all the time after Mariana Monteiro saw is that these cation effects must be also structure sensitive, right? Because they are very affected by electric field on the surface. So if you have different structures, the electric field they see at the specific potential can change. So I think that being able to quantify the surface structure, it's important to decouple at least one aspect that can affect the properties. So it's like the results you can obtain on a polycrystalline surface can change a lot if you move to a 101 or even to a 100. But if you are in not all polycrystalline surfaces are the same, so the results can vary. But if you can, you know what is your surface structure, I think you can understand better electrolyte effects too. I think it's just to the couple one aspect. So I think, in my opinion, electrochemistry is very simple, but it's the first step to be to really know that okay, this is the structure I have. This is my electrifying interface. Is reproducible. I control it. I understand more or less how the charge is changing with applied potential. I can go to the next step, and this can make the things a bit faster. So I don't know what do you think, Mariana or Reshma? So
I think it's like I said, for example, with Surface XRD, now we are sort of like, I'm trying to move towards these characterizations, the same as Reshma is also working on. But then we know how long it takes to get these 5 data points that I showed you now. And I'll now talk about then how to compare this with other surfaces, the reproducibility of these experiments. I think we still need to improve a lot on that.
What I also found beautiful, or what I always think about, is so surface XRD is a really powerful technique, but it's limited to crystalline materials only, as you also stated. So what combination of techniques do we ideally have to study all aspects, let's say, because maybe also the amorphous parts will play a role, or there might be an interaction between the electrolyte and the surface in a certain way. So what do we actually need to know specifically from these surface characterization techniques? How can we make it as encompassing as possible, that we capture all the aspects?
I think I can comment a bit on that, because it's also something that we are working on here at the department, and that's soft X-ray absorption. And if you use that, then you are sensitive to also the amorphous layers, and you can to some extent probe the ions, but also the oxygen. Of course, you have the oxygen of the hydration shell, oxygen absorbed on your surface. But I think, to me, at the moment, it's sort of like one of the techniques that you can get, I think, the most out of these interfaces. However, or XPS also, so operando XPS. However, if you look at the cells that we have to use for such measurements, this thin layer, the graphene coated cells, then you can wonder if what we measure is actually representative. So, like I said, I think there is a lot of room for development to improve these measurement techniques such that we can match the lab a bit better.
Yeah, I fully agree. Do any of the others want to pitch in? Otherwise, I have another question.
Adding on, like, we are also looking, for example, at surface enhanced FTIR to see the interfacial water structure. This is not complete picture because it doesn't tell you where the cations are, and I think a lot of this is maybe combining techniques. And I mean, it's exactly what Mariana said. For then surface enhanced FTIR, we are preparing the samples totally different from X-ray absorption, for example. So is the data comparable? Are we building up the picture of the same interface, or is it a completely different interface? It's all important questions.
Great. So there's a question from the audience for Mariana. So Shin asks, you investigated the crystalline material, but you also try to investigate polycrystalline materials and other electrolyte interfaces, so other compositions. I think this is related to the gold surface XRD.
So with the surface XRD, we can only investigate the single crystalline materials, or, for instance, nanoparticles that have very well defined single crystalline facets. So we cannot then there look at the polycrystalline, but all the work, I showed in the beginning was done on polycrystalline surfaces, so polygold and polycrystalline platinum. But still, I think if you think about the polycrystalline surface as a very, let's say, defective surface, looking at stepped surfaces, it's sort of like representative enough. And one could even think about looking at surfaces within the more defects and more steps. And according to also DFT calculations, ions should interact even stronger with the surfaces. That's actually why we went for gold 100, because that would give sort of like the largest chance of seeing something at all.
So you basically need almost atomically flat surfaces in order to be able to do this.
Yeah.
Yeah. I think it was mentioned before already, but cell design is very critical for all these studies that we do. And then this question arises: how representative is it indeed? So especially for Reshma, so with optical spectroscopy, how does the cell design affect the performance of your operando spectroscopy technique in also the time domain? Because you showed transient absorption spectroscopy, so you might get absorption from the water layer or changes in reflection. So how does the cell design also play with that?
So cell design is important, but I think it's not as tricky as, for example, the soft X-ray absorption measurements. So it's essentially we need something transmissive, and we have a water background. That's right. It attenuates a huge bunch of our signal, but that attenuation is more or less constant. So we are not changing that almost as a function of time or potentials. So if we just learn to live with that lesser signal, that's, I guess, the biggest issue. And water doesn't absorb a lot, so we're not dealing with like crazy, really thin cells or anything like that. So it's obviously not like a massive 3-electrode cell, but you're not on the microns or millimeter amount of water on the sample. So yeah, I don't know if that answers completely the question. So it's not as tricky.
No, I just wanted to provide some perspective on cell design and how it might impact different characterization techniques.
I think in my experience, and maybe Mariana has more experience also on this, it's the soft X-ray, or when you need to put it in a vacuum and interface electrochemical experiment with vacuum, that's when it starts to get really challenging. I think for things like hard X-ray or optical spectroscopy or FTIR or so that you do in ambient atmosphere, maybe it's not as tricky as when you're trying to have water on one side, membrane, and then ultra high vacuum. I think that's the tricky part.
Yes. Do you perhaps also have questions for each other? Because I can go on, but
I have for Reshma actually on the optospectroscopy, as we are on this. So I was wondering, because like, what is twofold questions. So one is like, what is the limitation in terms of material? Because you have to have this some degree of chromism in your material, right, for this measurement. But then also I was thinking, for example, if a ordered ion layer would change sort of the contrast or so at the interface, would you then be sensitive to that?
So in terms of like how we prepare the materials, we can go anywhere from single crystals to amorphous oxides. We need to have chromism, but most transition metals, at least the ones we might be interested in, have some degree of chromism. So all the manganese, nickel, iron, iridium, ruthenium. So most of the ones that we've looked at are fine and give us some kind of signal. We haven't gone, so we've only been very much in the development stage and haven't really started thinking about what happens with different ions and how that would change things, especially if you had like a large enough concentration. I probably would. I don't know how it would. It's an interesting question. But yeah, definitely something worth investigating.
Yeah. If you ever think of doing that, let me know.
Yeah. Yeah.
I have just a question for, it's more a curiosity and it's for Mariana because I'm a real fan of single crystals. So I wonder, why did you start to do XRD on gold 100 rather than gold 111? And how reconstruction is affected by cations?
That's a very good point. So the reason for using 100 and not 1011 to begin with was because at first we didn't even know if we would see something, like if the ion layer would be ordered enough to lead to a signal change. So I looked up and we had some DFT calculations showing that cesium adsorption on gold 100 is stronger than 101 and 111. So we thought, okay, let's go with 100 because higher probability. And then, of course, but then just like 111, 100 also reconstruct. So you have the hexagonal reconstruction. The good thing about gold is that if you just anneal it with a butane torch, you form the hexagonal reconstruction, so that's thermally induced. And then also we measured it in air before starting the electrochemistry with surface XRD. We can see a rod, like corresponding to the reconstruction. So we always can check if the surface is reconstructed. And then when we are in electrolyte at a certain potential, we can also always look for this peak and see if the surface is still reconstructed. Then we measure. And then sort of like, then you know that you are always measuring on the hexagonally reconstructed surface. There is also one of the data points I showed that we actually lifted the reconstruction, and then you can still see the cations like further from the surface, but that the surface roughness increases a lot. But yeah, it's very tricky because changes in the reconstruction lead to similar signals as changes of the ion layer. So you always need to make sure the reconstruction is not changing.
Great. So I think I also see now in the chat some more general questions, and it's related to what is good for your career. So I think we are still also very young people, but there might be younger people in the audience that can get some advice from you. So a question from somebody in the audience is what your experience is with different cultures and working in different cultures, and whether you think it benefited your career in the end, and what have you learned from this? So maybe I start with Reshma.
I think it's really important and really fun to work with people from different cultures. I think it helps you grow as a person, not just as a scientist, to know how different people think and how different people approach problems. But I think kind of having collaborations and working with people with different backgrounds is also important to be able to come up with creativity in science, right? Otherwise, we just end up doing more of the same. But you go to a new lab and see how new people do it, or even just chat with someone who comes at a problem with a different perspective. And that really opens up new ways about thinking about things. So yeah, highly recommend going to different places and doing part of your study in a new place and learning from different people.
So I hear, so different cultures, there's a cultural aspect, but it's also topic-wise, you recommend to talk to different disciplines and learn from that, and maybe switch fields from time to time, or is that, yeah, of course it's always a gamble.
Yeah. Yeah, I guess not. Yeah, don't. Well, I mean, it's also fine to go from biology to computer science or something like that. But yeah, just try look at how people in an adjacent topic will address similar challenges, right? And yeah. That's quite like for what we do. Solid liquid interfaces are pretty much everywhere. It's not just people looking at catalysis that care about these interfaces. So taking kind of inspiration from other fields that also still look at solid liquid interfaces, but maybe in a different context.
Yeah, no, I think it's great advice. Paula?
Yeah, I totally agree with Reshma, and then I will also add that it's good to time to change the environment, because you want to test the ability to adaptate to new environment where there is a different culture, where also the work style is different. I think this is something that is good to learn, that there are different work style, and this will build your future collaboration. And then also because in science, I mean, sometimes research is the needs in research are always changing, no? And so you have to also to change sometimes your research in order that this is it covers these needs or these demands. So I really think that, as Reshma say, working with people that has a different of knowledge, knows different techniques, can be very inspiring and can also guide you in your future research. Because something that I find very tricky in research is like thinking, what do you want to do, an idea, how do you want to continue, how do you want to answer fundamental questions, and how do you do it in a way that is different to others. This is very challenging, and this is something you don't get in one day, you get with the experience. So yeah, that's what I would say.
Yeah, no, I totally agree. I also think that it makes you flexible in the end, right? If you invest in this at a young age or early stage, because research is changing constantly. So there are new trends, there are new developments, and if you're really an expert on one thing, yeah, it doesn't make you very flexible to adjust to different environments and different topics. So I would also recommend it. So Mariana, do you have final words?
Yeah, no, just to add, I think a good thing of trying different groups and in different parts of the world is also, especially as a person in an early career, to also see what you like and what you don't like and what is your style. And I think I really praise like being happy in the work environment, and for that you need to experience different things to see what you like and what you don't like. And then also, if you become a mentor, how do you want to lead your student, basically?
Yeah. No, also there, I think it's really important to get familiar with differences in culture and differences in mentoring style, because every person that you work with requires a different approach in the end. At least that's what I now encounter. So, so there, I think it's great advice. So last time, I think somebody asked Rafaela specifically what she is encountering as a female scientist. Now I have very talented female scientists in front of me. So can you also comment on that and what is needed to boost this even more? Or can you give your vision on that?
Yeah, I guess I can start on a positive note. I think there's
Yes.
many younger female scientists now, and there's great friendship and positivity between. I mean, everyone supports each other, and so things are changing from maybe what they were 20, 30 years ago, and it's a much more friendly and positive atmosphere. And I think as the younger generation of female scientists starts to go into more leadership roles, and they start to become hopefully role models for the next generation, and hopefully that feeds through to more women taking up science as a career. But I feel it's quite an optimistic time now, more than what I felt in the last 10, 12 years or so.
So it's progressing in the right direction, you feel?
Yeah, I think so. I mean, progress might be slow, but at least it's moving.
It's going in a direction, and it's the right one.
Yeah.
Do the others want to pitch in?
Yeah, no, I think my experience, and it's also positive, and it's what Reshma said. I think now it's the right time to be a female in academia, I would say, because at least in a starting position, because there is a lot of opportunities that are appearing, and universities are more and more pushing for this. Although I would still say, if we talk to more, let's say, senior people, the numbers are still low. But I think maybe like our generation is the generation that will change that. So we need time to get there.
Yeah, I agree with Reshma and Mariana. Actually, I mean, in general, my experience has been positive because I have been always like supported, no matter what, no matter the gender, and I think we are in the good direction. Maybe it's true that in general there is a little bit less female representation in some fields, but I think this is changing, and I think that in the moment we have a little bit more representation, maybe, yeah, everything will change or go in the right direction.
Great. I think also in view of time, it's time for some final words. So thank you a lot for all your viewpoints and your vision on this topic as well, but also for your wonderful talks. I think what I take from this is that it's important to keep stimulating each other, to keep supporting each other between gender, between discipline, between everything. So try to look outside of the boundaries of whatever you're working in. And with that, I want to end with some advertisement. So I will share my screen again. So first of all, we have certificates for you. So to show that you gave this talk and that it was well received by the audience. So for Reshma, Paula, and Mariana. And as I said, so these youth talks are weekly. So next week there's another one. So June 20 on Tuesday with this wonderful lineup. I unfortunately cannot read Chinese, so I cannot pronounce their names at this point. But yeah, if you're interested in carbon neutrality and scientific machine learning, please join also next week. And then, yeah, I want to thank ICANX for the wonderful organization, this wonderful platform, for this opportunity. And thank you all for joining this session. I hope you enjoyed it. I had a good time, and see you in the future.
不再是奇迹，不再是幻想，此刻真感觉全世界为我鼓掌。不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞。不再为曾经失败放弃或感伤，努力才是真的方向。I can， I can， 没有什么可以阻挡心中无限的